Okay, hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. We are going to do one more day of raycasting programming, just because people seem to like it from yesterday, and so we figured we'd do one weekend of it. And that's about it. Next weekend we will return to Handmade Hero as normal, unless something catastrophic happens, which I'm not willing to rule out based on how much trouble I had getting this streaming setup to work, even though it should have been simple. So let's take a look at where we left off from yesterday. Oops, that's for Unix. We're not on Unix right now. Let's go to the Handmade Ray directory. This is what we wrote yesterday on stream, and you can see if I open up the project here, it's a very simple two-file project. There's like an H file and a CPP file. Let me go ahead and show you those, and I'm running it right now. You can see it raycasting over there. What you can see is we just have a really simple program, very, very straightforward. All it does is set up a little, world model here that's got some materials in it, with some planes and some spheres and so on. And then it just has a simple raycasting loop. It goes through and asks this little raycaster here to trace some rays for it. The rays, this is really, I don't know why we call this ray count. It's really bounce count. It's how many bounces the ray has done. It has nothing to do with ray count. So it's how many bounces the ray has done. It just goes through and casts a ray. It looks at all the planes and spheres in the world, sees if it hits them, takes the closest hit, and then processes the material on that hit. And that's it, right? We write out a bitmap at the end here, just a simple bitmap image that we can view. And we made a batch file that runs the raycaster, which you see running in the left-hand side of the screen. And then it outputs the final image, which you can see here. Right? And that's about it. So what I'd like to do probably today, I think, is we've got sort of two things we need to do to this raycaster in order to make it like a useful raycaster. Really, technically three, but the third one I don't know that we'd ever do. I mean, maybe we will. But this is just kind of a toy project that people wanted me to make, so I made it. So I don't know that we're really going to try and make it into something much more than that. But those two things are better material processing, right? Because right now we don't really do light transport for real. It's not physically simulated. We don't have a real material model. We're not like handling like the Fresnel equations or any kind of real computation of what happens when light hits a surface or transports along a ray. And so the results, while they look sort of pseudo-real, like they have some of the properties that you might expect from real light, there's a bunch of like errors in there about how it's being computed. So the results just aren't very good, right? They're not gonna provide that like realistic look that you can get from a ray tracer without too much effort, as long as you obey the correct physical equations. So that's something that's worth doing, and some weekend we'll do that in the future. The second thing is just making it properly SIMD and parallel, which is something that makes the speed work well. And that's something we really want to do because, especially once you start working on adding better lighting and that sort of stuff, and you want to test it, you don't really want to sit around all the time waiting a long time for the results to see what worked and what didn't, or any of that sort of stuff. So we'd also like to speed up the ray tracing considerably if we can, and decrease that turnaround time. So optimization is the other one. Those are the two big ones. And I'd like to do both of those. I think I might do optimization today, or try some optimization today, like try to get threading working, for example. Now, the problem that we have with the third one, which is one I probably don't want to do, that would make this a complete ray tracer you could actually use for something, is some way of loading real scenes and creating an actual spatial accelerator, right? And that one is a much more complex undertaking. So that involves picking some kind of file format, like, wavefront OBJ files, or I don't know, some kind of an interchange format. There's a lot of them out there. And reading in the data from that, which is probably going to be triangle meshes or displacement meshes or something. And then processing those into a raycasting format that is binned so that rays don't, because we're going to be loading, like, at that point, millions of triangles or something. You can't test every ray. It would, you'd be way too slow. So you need a spatial acceleration structure that allows rays to only test triangles or scene elements that they may come close to hitting, rather than all the ones in the scene. And if we wanted to increase the number of spheres, we would want to do that as well. Like, the number of spheres in here is very tiny. If we wanted to increase the number of spheres to, 100,000 spheres or something, we would have the same concern, right? We would need to put in some kind of spatial hierarchy to reduce the number of sphere checks we have to do per ray test in order to make it run reasonably. And that's a whole nother sort of huge undertaking. That is the vast, vast, vast majority of work in a real raycaster. Is that is where the work is. The work is not so much in the light transport parallelization stuff, because that is just more well understood. It's usually that bounding hierarchy, building the bounding hierarchy quickly. What kind of bounding hierarchy is most effective? Usually KD trees. How to test triangles efficiently with, look them up and gather them quickly, the ones you need to test. How you deal with the fact that you're trying to do SIMD, but different people are looking at different triangle lists, and blah, 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 blah. It's just very much a serious programming undertaking once you bring that into it. So I'll probably skip that part, since this is not the main focus of Handmade Hero. And we'll just focus on the other two, which I think we can do relatively simply. And I'll take the easier of the two today, which is just figuring out how we're going to do some sort of optimization for this. So if you take a look at what's going on here in the code, you can see already, the slowness of it is largely becoming from this rays per pixel. Because if we set rays per pixel to 1, it would finish almost immediately, right? And you can see the problem of having rays per pixel being 1, and that is that we don't get enough samples to really get a smooth image. Now, we get roughly a correct image, right? I mean, we are producing something that looks reasonable, because, one ray does produce a reasonable result, but it's just not a smooth, nice, continuous image like we would like. And there are a lot of ways of producing better results even from lower sampling rates, and that's something we can look into in terms of when we go to start doing the lighting sampling and stuff like that. There's ways of using better reconstruction from the samples that you do take, and also in figuring out how you take your samples. There are ways you can improve the quality without improving the number of rays. And so again, when we start to look at material stuff, that's something we can look at as well. But for right now, what we want to do is just set up the structure of our program a little bit better so that we're getting more performance in terms of just how many rays we do take. So for example, if I raise per pixel 1 and I switch to rays per pixel being 8, you can see that the difference in speed is already pretty dramatic, right? And, it's probably roughly 8 times slower. Now, how much slower is it? Well, it would be nice if we actually knew how much slower it was. So I think what I'm probably going to do here is I'm going to first introduce a timer so we can actually see how long we're taking as we go. Now, because we're timing an entire raycast, we don't really have to appeal to Windows functions yet. We can use a low-grade timer. So we can take a look at the C runtime library again and look at the functions involved there and see if there are any that will be good enough for us. So for example, the time function is one that's available everywhere. And this returns the number of seconds elapsed, for example. So we could get the number of seconds elapsed pretty easily from the C runtime library. And since our things tend to take multiple seconds, that could be enough. There's also other functions that might be reasonable that could give us a little bit more resolution. Unfortunately, I don't know how many of them are portable. For example, the utime functions. I'm not sure. That's not what I wanted. The utime functions are for files. Do we have anything slightly better? Time management, clock. So clock is clocks per second, which might be reasonable. Let's just take a look at what it is. That may give us a little bit better resolution. Here we go. let's do a printf here. Per sec. I don't know what clocks per second, what the clock t value is actually defined to be. So I'm not sure exactly how I would print it out, but what I can do here, if we want to, is I could find clocks per second, and in fact, why don't I just go ahead and do that? So if I open up MSDev, actually we have a project that we had created for this purpose, but I think we didn't copy it to the new machine. I'm just going to create a Windows desktop application here using the stupid application wizard. And I don't care where it puts it. So this is in Windows Project 1 in some users Casey source repos. I don't care. I don't care where the stupid wizard puts it. It doesn't matter. All I want to do is get the browse info thing working that this thing builds by default, right? And so what I can do here is I can say clock t in this project, right? Why is it capitalizing that? Like so. And then if I take a look at this, I should be able to do a go to definition. Now it can't locate it, but I assume that's just because I haven't included the right file. So if we take a look at what it requires for a clock t, where was that at? I had that a minute ago. Here it is. I assume, yeah, it's just in time.h. I assume that if I just put time.h in here, right, as an include file, and save that, then it should be able to find this. And hey, lo and behold, it does. So if we take a look at it, it's just a long value, which means I can print it out with a %d just fine. So if I come back here to our Ray program, I should be able to run it and see what the clocks per second is. Now, I'm getting the same error here, but that's like rather obvious. Why? I need that, what was it called, time.h? I need that time.h. So you can see that the clocks per second, it looks like there's 1,000 clocks per second. That means it's a millisecond clock. That is fine for our purposes, right? Because we're timing huge loops here. So the fact that this is a fairly low resolution timer, I don't care. I'm totally fine with that. That will be fine for our purposes, and it will remain platform independent, which I'm kind of trying to do on this project so that we don't have to have additional libraries or anything involved. How we're going to do threading that way, I don't know. I don't really want to use standard thread, but maybe we might have to. That's going to be the worst thing that's ever happened to me. But okay. So if we take a look at the start time, here it looks like we could just get this by calling clock, like so. And then we can make an end time by calling clock here. And then we can just sort of go through this. Excuse me. As we start our loop, we can just go through the loop, and we'll ignore like the right image time. So as we get a start and end, and maybe I'll call these start and end clock. There's our start clock, there's our end clock. What I should be able to do is say, okay, here's the number of milliseconds that this took. Let me go to the other pane here so we're not getting up up into the Casey's head area. If I take the end clock and the start clock and difference them together, I should get how many milliseconds it took to do the rate casting, right? And so, you know, there's the image. It looks like it took 2,059 milliseconds, so that's a pretty easy way for us to determine how long it took. And furthermore, what I could do is count the bounces. So if I introduce here some kind of a global variable, I'm just going to define global variable term there, just again so I can see it. If I introduce a global variable here that's like how many rays have I cast, I'm going to say like so. Well, you know what? I don't even have to make it a global. I could just put it in world, actually. Let's just do that. If I go ahead and accumulate how many rays are cast, then I can have some idea of what's going on, right? So if I come in here and say every time I enter this loop, I'm casting a ray. So I will go world rays cast. We can say how many, or I should say like bounces computed, or like, let's call it that. So I need some way of printing this out. And in general, I always forget I think it's LLD or LLU, I guess, for a U64. I don't really remember. Let's take a look. Also, let me go ahead and grab from Handmade Hero the U64 definition. I think it's standard def that has these in there. Oh, I forgot about standard def this whole time. I actually defined these myself, but I didn't really need to because we are using the standard library. So I guess I shouldn't have bothered with that. I guess I could have just done uint 8t. Can I do that now? Uint 16t, uint 32t. You are, int 8t, int 16t, int 32t. I forgot about this. Oops, I don't need to change that one. So yeah, in theory, I can just make 64-bit types here without having to do anything fancy. And then we can count the total number of rays, even if that number comes very high, in theory. Oops. What is this complaining about? Doesn't standard def include these? Did I mess something up? Oh, it's standard int. My bad. There we go. All right, so let's see where we're at here. Let me go ahead and finish this up. There we go. So now we should get a thing that says how many bounces we have. Don't ask me why the millisecond number is in there. Here's how many bounces we did. Here's how many rays we cast. Put this in here. So that's a little cleaner. So now we can print out the number of milliseconds per bounce or something similar, right? So, you know, the performance was, you know, point something milliseconds per bounce. So if I go ahead and say, all right, we've got a total time like so. So we've got a time elapsed. This is the number of milliseconds that have elapsed. And then we want to take how many milliseconds per bounce. I just divide the number of milliseconds by the number of bounces. I'm going to cast them to doubles so that we'll get because it's going to be a fractional number. Then we should be good to go. So there we go. So now we can sort of see how many milliseconds per bounce we're taking. Right? And our goal, obviously, is to drive that number as low as possible, as well as the total raycasting time as well. Now, in theory, that milliseconds per bounce number should remain relatively constant. I mean, it's not going to be perfect. But for example, if I was to crank up the number of rays to pixel to 16, you know, here's the number of bounces we've had so far, right? So, you know, we're looking at this number. If I recompile it and rerun a slower one, you know, the total time will change. right? It doubled roughly, but you can see that the performance number was pretty darn consistent, right? So as I increase the number of rays, I can make the total time slow down. But if we just look at how long it's taking us in general per bounce, that number should be roughly the same, and you can see that it does. And that's why I divided those out, was just because we're a little bit early in the process here, but it just gives me a starting number I can look at to see whether I'm making some progress or not. And driving that number down, I can fuss with different things here and change which images we're creating without having a huge effect on that number, which is good. So that way I know whether, I have a sort of a stable version of the performance there. Okay. So let's start by taking a look at how these loops are working here. We are already compiling in release mode to a certain extent anyway. And we don't need these handmade defines in there because there's none of that that's happening now. So we're already compiling in release mode, so we're already getting some performance. The compiler's already doing some basic stuff here for us, and that's all good. But there's a bunch of stuff that we need to start thinking about now in terms of what we want to do. So the first thing I'd like to do is I'd like to break this up into image chunks, right? I'd like to be able to, in a little bit, hand this off to, let's say, I think this machine handles 8 threads simultaneously. If I remember correctly, let's take a look. Change graph to logical processors. So this is a 7700K. It's a 4-core machine. Each core has 2 hyperthreads. That's why you're seeing an 8 wide graph here. And hyperthreads, in our case, may or may not help the performance significantly. To be honest, I'm not super familiar with the 7700K Core i7. I don't know to what extent ray tracing is going to saturate the arithmetic units on a single core. We are not under memory pressure right now. We are not only not modifying any memory at all, but we have very little memory to read. So all of it's going to pretty much fit in a very small cache. It'll probably just stay in L1 the entire time, would be my guess. The only thing that wouldn't is the output image itself. So I think we're looking at a situation where we're probably going to be able to get the memory traffic down quite a bit, which means that the hyperthreads are not going to be covering for latency bubbles. One of the things that hyperthreads often do is hyperthreads will allow you to cover long memory latency bubbles by giving, one thread will execute inside the other thread's memory bubble. While it's waiting for some memory to come in, the other thread can execute and use the ALUs and whatever during that time. We're probably not going to get much of that because we don't have very much to read from. In a ray tracer that actually was using a real scene, we absolutely would, because a lot of that time is pulling in stuff from the bounding volume hierarchy and getting new triangles into raycast against. So that is not necessarily the case in a full ray tracer, so take that with a grain of salt. But in our case, we're mostly talking about trying to use the ALUs, I think. And so I don't know whether or not we will really be getting much mileage out of it or not. We will find out as we go. So we'll see. But either way, even if we weren't going to get anything out of hyperthreads at all and determined that we wouldn't, which is probably not the case, but let's say we completely weren't able to get anything out of the hyperthreads, we still want 4 threads operating at the same time, right? We want to have 4 threads doing things at the same time. Now, there's a couple different ways that we might want to do this. And again, it's a little bit tricky to think through exactly how we want to do it because as we go a little further in how we're going to do the ray tracing and so on, we don't know whether or not we really want to separate out into pieces of the image or not. I suspect, though, that we probably do. So I think what we probably want to do is just divide the image up into little chunks, and possibly, if we're going to be operating on those chunks repeatedly and summing together the results, we may even want to make the chunks small enough that the output stays inside of the cache. So for example, the L1 cache is 256K. If we were summing up samples in there, we may want to try doing, if we're outputting them successively, we may want to try to keep the size small. Right now, we're just summing, we're doing an entire pixel completely first, rather than producing intermediate output images as a preview to the user. So right now we don't really have to care about that, and we know that we're not having any cache problems at all, I think, because there's really just nothing to load. So I don't know. First things first, I'm just going to divide us up into some tiles to do so that basically every CPU core can have its own tile that's completely separate from anyone else's tile, right? So that's what I'd like to do now. And because I'm going to do this in a way that's more like what you would do in a real ray tracer rather than take advantage of the fact that we don't have a bounding volume hierarchy. Normally what you would do is you use tiles that are square shaped, and the reason for that is because you assume that the kind of traversal through the grid, the bounding volume hierarchy, will be more coherent in a square than in a row if I just gave every CPU a row. Because you figure that rays cast in a similar direction will hit similar things and bounce in similar ways, potentially. Now, that's only true to a certain extent. When you have a lot of diffuse surfaces, rays tend to bounce in all directions, and that doesn't always happen, but you still will probably get more in a square than you would otherwise, although it won't be that much more as it is if everything was perfectly coherent, obviously. So, anyway. Sorry to dump too much information on you there. Anyway. So what I'm going to do here is I'm just going to break this up into a couple different tiles. So what I want to do here is I want to introduce a function that I can do, which is sort of like render tile, right? And that will take one of these saucy fellows here, where you know, we'll sort of grab, you know, this sort of thing. Like this, and we want this render tile function to take the range for X and Y that it's actually going to use, and it's going to need to be smarter about how it writes to the output value because of that, right? This line can stay the same because X outputs will march along uniformly, but Y outputs will have to do something different, right? So we need to make that change as well. So for example, where is the output pixels line here? It's somewhere. Right here. So this line will have to change, but everything else could probably stay the same. All right. So what I want to pass in here is like the Y min and the Y count and the X min and the X count, something like this. And I might do this, maybe I'll do this like this. And I also want to pass in the image that we're going to write to and the world. So I'm going to say raycast this world into this image, and I want you to just do this tile, right? So this Y here is actually going to be like, hey, start from Y min, or actually I guess that won't quite do it that way. You know what? Why don't I just do this? Why don't I do Y min? So we'll do it like this. So this will basically say, let's do a subset of the image. Again, the X will work just fine inside its loop, but the outer Y loop is going to have some specificity to it. So the first thing we need to do is we probably want to do a thing that's like get pixel pointer. And we want to say like, hey, give me the pixel pointer at this location. And that'll move the pixel pointer to the right place for that X and Y min. And then what we need to do is every time we do the Y, we got to go. And you know what? We probably don't need to be too specific because the inner loop is going to be so costly. It's OK. We can probably just use get pixel pointer here, where we say, all right, get the y, X min and the Y that we're on right now. Just give me that out pointer, and then I'll increment along it, right? All of these equations should, in theory, now stay the same. There shouldn't be anything weird going on there at all. And so if I go up here and just implement this get pixel pointer, function. What I should be able to do is just compute where the pointer would be in the image. So I know I have an image. Here's the pixel pointer to the image. I know that I want to go X pixels in, and I know that I want to go Y pixels up, right? So I just need to multiply by the width to move me up Y pixels, that number of rows, and then just use the X, I'd probably write it this way, just to get me to the right X, right? But that should give me a pixel anywhere in the image, and off we go. Now, sorry, what is this complaining about? Left of pixels must have a, oops, that's what I didn't want that there. There we go. In fact, I can just do this. And we need some of these other values to be computed in here. So half pix W, that sort of stuff. All of these sorts of things. I think all of this stuff wants to be up in here. There we go. And the camera we need to pass in as well. Now the camera, at the moment, since we don't care, I'm going to let that happen up in here as well, because we're not really fussing with that yet. In the future, we probably want that to be passed in as part of the world or something, right? But it doesn't really matter. Raycast cannot convert argument to, there we go. Let's get that going. All right. So now we just have to, as you can see, we don't get any image now because we're not calling this. But what I would like to do now is I'd like to actually call this raycast function to render the world, like so. And I'm just going to do image width, image height, and have it just render the image as it was rendering before. And if we didn't mess anything up, we should just get the same image, right? And it looks like we basically did. That looks right to me. And so now what we want to do is say, okay, can we break this up into multiple tiles? Now, yeah, I don't have a way of getting the number of CPUs here, but I could pretend that I did. So let's say I said core count equals 8 here, and maybe if we wanted to add something in the future that could query the number of logical cores by calling Windows, since we're not calling Windows right now, I don't want to do that. But you know, the user could say maybe the core count then that they want to use. What I want to do is I want to break up the image into that many tiles, right? And so I guess the other way we could do it is just use a tile count. I don't know. We kind of need a core count though. So let's go ahead and say that we could specify a core count, and then we might have a tile width, tile height kind of a situation, right? And we want to compute what these are. And so maybe what we say is maybe we want to just take however many cores there are, and we want to kind of break up every row into that many tiles or something. I don't know. I'm making this up. But let's say we took the image width and we divided it by the core count, right? And let's say we wanted to round up so that we wouldn't have too few, we'd have too many if it wasn't an even divisor. So let's say we took the image width and we added the core count -1, and then we divided by the core count to give us a number that we knew would sort of like get us to the end of a row always. And let's say we always use square tiles, so we have tile width and tile height equaling the same amount. Let's go ahead and print that out. So here's the configuration. Make cores with %d by %d tiles, right? So just so we can see what it is, so here's our core count, here's our tile width, oops. So we can actually see what that ends up being. And then what I'm going to do is just render one of those tiles. Right? And so that's it. That's all I wanted. You can see this is 160 by 160 tiles. And you know what? Maybe I'll actually also put the bytes per tile in here, or the K per tile. And what that's going to tell me is just how big the tile is relative to the cache. Now, again, it shouldn't matter because we're not actually updating tiles in any particular way, but I'm just going to print it out anyway. So that's tile width times tile height times 4, or size of view 32, divided by 1024. Oops. What is it? Oh, because of size of. All right, fine. So now it'll tell us like, okay, it's 100K per tile. That would fit in the L1 just fine because it's 256K L1 on this particular chip. So there we go, right? And we know the world is pretty tiny as well. We could actually print out the size of that if we wanted to, but I think we're basically good. So now let's just make a loop that will render all of our tiles for us. Right? Like so. So here we go with this render tile function. We just need to go, okay, we've got tile index, or tile x. Tile x is less than, well, actually, I guess I don't know how exactly I want to do this. I guess we could just say what the tile count was. I'm not sure how I want to do this exactly. We'll see. We'll see as I write it. So what I want to do here is say, all right, let's suppose that I'm going to go over all of the tiles, right? And what I want to do here is I want to say that I'm going to produce the min y, and that's going to be the tile y times the tile height. Right? So as we go through here, I'm going to I'm going to basically, what, I think I can just figure this out ahead of time because I can just do the divide and round up and then I know that's how many tiles there are. So it should be pretty straightforward, right? In fact, I don't really even need to quite do it this way because I mean, I could just do the straight divide without rounding the divide up as well, and it wouldn't matter. You just have a fractional at the end. So the rounded up version is just saying like, hey, 160 times 8 is 1280. It gets the, well, I'm always going to get that much. Even if we had an image that was slightly bigger, it would bump the tile size up so that we'd only have that many. We'd only have the core count. Number of tiles there. So, but I don't really know that we care about that. So maybe I'll just won't care about that for now and just say, we'll just do this. And then what I'll say is, let's compute the tile count x and the tile count y and just know those ahead of time. Right? So the tile count x is just going to be however big the image width is divided by the tile width is going to tell us how many of these we have to do. But that would be if we skipped like any remainder. So this is where we want to do sort of a plus tile width -1 thing to make sure that we count for the remainder. So we'll get an extra tile that's like smaller if we need it, right? To fill in the gap. And the same is true of the height here. So there we go. So this way we can know that that's going to cover the entire image. When we do the min x, min y, those are just going to be straight multiples. So we know that our minimum y is just going to be however many tiles we've gone times the tile height. Same with the min x. The max x, on the other hand, is going to be the min, we take the min and go 1 tile height forward. That would be how big it would be if we didn't ever have remainder tiles, but sometimes we do. So if max x is going to be greater than the image height, we need to clamp it, right? We don't want to, in other words, if we have a tile where we need to do a fractional tile to fill in like the top row of the image, we want to clamp it down so we don't overwrite the image, go further out of the image then there actually exists image, right? Don't ask me why I wrote X there. So here we're computing those values. We now can use those values. Here's the min x, min y, max x, max y. And I really, sometimes I just like to be careful about this and say it's really one past the max x, because it's not really the maximum x value. X will never take that actual value, right? It's one past max x. And so sometimes I just like to say that so that it's clear. Because again, the loop doesn't actually use that value. So it's important to note, right, because it's a fence post error otherwise, we never compute the actual image.height row. That is one past the last row. The last row is image height minus 1. That's the index for it, right? So sometimes I just like to say that. Anyway, oops, let me do that. So now we're doing each of those tiles separately, and it looks like that reassembled properly, which is nice. We now have a problem, which is like this printout is kind of printing out in the wrong place. I don't know how we want to print out %done yet. That's kind of a tough one. I guess we could just print out how many tiles we'd done, but that might be a little too granular. I don't know. I mean, let's try it for now. And we'll see how it goes. Something like this. Maybe even total tile count equals tile count x times tile count y. And then in here, I'll just say tiles retired divided by total tile count, right? So that'll just print out that percentage and let us know how far we've gone. And yeah, we'll just keep track of how many tiles we've retired. Tile retired count 0. And so every time I render a tile, I'll do tile retired count plus plus, and off we go. So there you go. That looked a bit strange. Oh, right. That needs to be inside this loop. There we go. So there's the tiles as they retire, and there we're done. So that's fine and dandy. Now we know we can do this in tiles, and we've got one or two things that are slightly busted at the moment. Here in our world structure where we've got bounces computed, and I'm going to do tile retired count in here as well. I'm just going to go ahead and put that in the world structure, and the reason I want to do that, we'll see in a second. Where we go ahead and do, where's that bounces bit? Bounce computed. We'll put tile retired in here. I'm going to move these to the end, so when we complete a tile, we're going to take the bounces computed and put it in here. So what I want to do is locally in here use a local variable that's not in that structure for bounces computed, and I'm just going to add in here every time we do a bounce. I'm going to increment that. I think it would be sufficient. I mean, I'll make it a 64. It would probably be sufficient to do a 32 inside here because it's just in the tile, but who knows? Maybe it'll overflow. We don't want to guarantee that. So we'll just make it be a 64 and we'll do it here. At the end, we'll sum these two together for our statistic gathering purposes, a tile retired count. And then in here, when we print things out, we should be able to print out the correct values, I think. Oops. Of course, I have to actually get them out. Here we go. Piling up preview windows here. There we go. And world is a dot. What else we got? What else you got for me? Oh, those were all from one thing? Jesus, okay. That is a pretty bogus value. What's going on here? Tile retired count times 100 divided by total tile count. Total tile count is valid. Tiled retired count is a U64. I mean, it's a U32. Why did that get grumpy all of a sudden? I must have missed it. Let's take a look. It slipped by me. Here's the raycaster. I'm going to switch real quick to debug mode. So you can see that this value is highly bogus here. I'm going to go down here and take a look. I don't really want this to keep going. I'm going to kill it. End task. Okay. And I am going to go ahead and compile. Oh, no. I did it again. That. I just want to run it from here. All right, so when I run it from here, I do not know why this window insists on continuously coming up, this diagnostics tools things. I think we just want to kill it because it's bugging me. So I want to look at the world structure. You can see the tile retired count is 0 here. I'm going to go into one of these, and I don't really want any of this stuff. So let's just go to the watch. Here's the tile retired count. I'm going to do rendered tile. I'm going to see what that actually... So tile retired count gets incremented by a huge number there, which isn't what I intended. So I probably just put that in the wrong place. Oh, I put it... Well, that would explain it. I put it in raycast. Don't ask me why I did that. So yeah, inside render tile, I really want it in here is where I would like it to be. When raycast returns this value, what I would prefer is that since this bounce count is like pretty low here, I would like this to be returned as part of the raycast. And really, this can be inlined inside of render tile. It doesn't actually need to be its own function call, because really it's just this loop here, right? It's just this thing. So if we want to, we don't really need this to be a separate raycast function. And I don't know that I want to inline it like that for now, but it's hard to say how I want to do it. You know, I sort of do, I sort of don't. For right now, I'll cheese it. I'll go ahead and say bounce is computed. Well, yeah. You know what? I'm just going to inline it. It's going inline. That's what's happening. So raycast is going away. Goodbye. So here we are. So inside contrib here, so you can see we've got kind of our ray index happening. We compute all these values here, and we compute our ray origin and ray direction. Then we go through the bounces, and we'll do our bounce computed there. This will come out to the outside, and we'll do our bounce computed that way. We'll go through each of these computations, and in the end, we will do our color sum this way. So here's where we were doing the raycast before, so we'll get rid of it here. We have this contrib value, which is the amount that it will be contributed to. So what we can do is just come in here and say color equals contrib times Hadamard. There's that summation that we need to do, and that should give us what we need for color, right? We don't need result there. So that should give us what we want. Right? And if we needed to, we could also sort of separate those out a little bit more cleanly so that contrib is multiplied once at the end rather than every time here, which does kind of seem like a little bit better. So what we could do is say that when we get the color out, it's like as it's summed up. At the very end, we just do a color times equals contrib sort of a thing. And then at the end, well, color plus equals something like that, right? So that way we have sort of two separate things. We've got the, the result here, and we've got the sample. This probably shouldn't be called color. This should probably be called like final color or something like that. All right. So let's see what we've got here. Did I say that was a V4? That was my mistake. All right. So now we've kind of got a closed loop here, which should be about right. Bounces computed is now going to be accurate, I think, and we retire both of those things here with the tile. So that's good. Let's wait till that finishes up. Okay. Come on, Mr. Raycaster. Don't make me kill your task. I'll do it. There we go. All right, so so close. All right, so the sample is summed here like so, and the final color is summed in here. That is how that should work. I am going to kill you this time, Ray. And now I think we're good. There we go. Okay, so now we're pretty good to go here. Most of what we have does what we need it to do. Our problem now, as you can see the way I've set it up, our problem now is we want each of these render tile calls to run on a separate CPU, right? That's what we would like it to do. So rather than calling render tile like this, what we would like to do is basically push these tiles onto a list, and then we would like to dequeue them from the list as we go, right? So, that's the goal anyway. So what I'd like to do here is say, all right, we've got a total tile count. I'm just going to record all of the ones that need to happen into a queue, and then I'm just going to have that queue sort of ready to go that can be processed in a multiprocessing environment, right? So I'm going to have like a little work queue thing here. And it's going to store the stats so that world is now separate. And it's also going to have a work order. And that work order is just going to store the things that we needed to do to render the tile, right? So what we're going to have here is essentially all of this stuff here. Here's the output image. Here's the xmin, the ymin, the one pass, like all this stuff is just going to be in there like that. And then the work queue is just going to have some number of these. And all of this stuff is going to become multi-threaded. So I'm going to label it as volatile. And what that is instructing, just so we're clear, when we went over the stuff on Handmade Hero, for some reason, and I do not know the reason, not only is everyone on the internet wrong about what volatile does, but everyone who ever writes into me about volatile is also wrong about what it does. And I do not know why. It is the simplest possible thing to understand. Please just trust me when I tell you I am not wrong. Volatile is an instruction to the compiler that the value may have been changed by someone other than the code generated by the compiler. That's all it's doing. It is required for multi-threaded programming because otherwise the compiler may not reread the value when it has been changed by somebody else. So it's required. It is not sufficient, meaning labeling something volatile does not make the code work multi-threaded. It's simply required to make code work multi-threaded. So if you have a value that multiple threads may touch, you probably need to call it volatile. Now, there are times that you don't need to call it volatile. And the reason that sometimes you don't need to call it volatile is sometimes the functions you use to operate on them imply volatility. So if you use a locked increment function, it may have the notion of volatility baked into it in some way that forces the compiler to treat it that way. It can't hurt to add another volatile, however. So in this case, I'm going to label these volatile. And the reason that I'm labeling all of these volatile is because when we go to make this multi-threaded, each of these values may be touched by multiple threads. None of the other values will ever be touched by two threads at once, ever, right? And when I say touched, I mean written to, right? And so as long as you're only ever reading and writing values from a single thread, even if there's thousands of threads operating, any value that's only read from and written to by a single thread, that is not volatile, right? The only things that need to be marked volatile are things where inside a particular operation of a given thread, as far as the compiler is concerned, some other thread may come and touch the value. That needs to be marked volatile to prevent the compiler from caching its value in a register and not reading it back, for example, right? Because that is something the compiler will do, right? The compiler may, like let's say we're looking at next work order index. The compiler may go ahead, or bounce is computed, right? The compiler may go ahead and pull bounce is computed into a register, operate on it a bunch, and then put it back out again. Well, if another thread might come along and also change bounces computed, now that value is wrong. Even if our multi-threading is correct and everything works exactly as it should, the compiler's caching of the value in a register will create a bug in the code that wouldn't have been there otherwise. And that is what volatile prevents. Volatile prevents register caching or stack caching of a global, and it doesn't have to be global in the C++ scheme, but in a visible from multiple threads value that is changing on more than one thread at a time, right? So accumulators are generally where that happens. All right. Please just believe me when I say that. I really don't want to get another 100 emails from people who don't know what volatile means, telling me that I got it wrong, because I didn't. That is what it actually means for real. That was very annoying the first time we went over that on Handmade Hero. I don't mind getting corrected by people who know what they're talking about, but that one was particularly bad, where hundreds of people were trying to correct me on something that was correct. That and the locked increment thing, you don't know how many people wrote to me telling me there was a race condition in Handmade Hero and there wasn't a race condition, and I have to go back and forth on email like 20 times with them, like, no, that's not a race condition. This is how x64 works. This is how locked increment works. This is not a race condition, right? Like, it's good to get, I guess I should take the good with the bad. It's good to get people who actually tell me when there's a bug in the Handmade Hero multi-threading code. But the problem is, for every one person who correctly identifies a problem in the Handmade Hero code, most of the time people write in and they're just right. It's like, oh, here's the thing I found. And I'm like, oh, yeah, that's wrong. For some reason, multi-threading is like unique in that tons of people seem to think they understand it well enough to point out a bug in someone else's code when they actually don't, and there is no bug. And I don't know why that is. I guess it's just poorly understood topic. It's weird. Anyway, so here we go with render tile. I'm marking these as volatile now because I know they will be volatile because multiple threads will operate from them. My work queue, I'm just going to basically make an array of work orders. I know exactly how many there are ahead of time because I know how many tiles we've broken the scene up into. So what I'm going to do is, when we start, we have a total tile count number here. I'm going to go ahead and set the world. I'm going to go ahead and create a work queue. Here's my queue. I'm going to clear it. I'm going to set the work order count to be the total tile count. I'm going to set the work orders to be an array that will have the correct number of these. So it's going to have the number of work orders that they're supposed to be in the queue. It's going to have those like so. And then what I'm going to do is I'm going to, each time through this loop, rather than calling render tile, I'm just going to move that render tile out here into a different for loop. And instead, and this is going to print out the status here. And what I'm going to do here is, for these tiles as we go, I'm, instead of actually computing any given tile at a time, I'm just going to take what I would have done to compute the tile, and I'm going to put that into the work queue. So I'm going to say, here's the work order, right? And in fact, you know what? I could do this as just a, oops, that's good. I can do this as just a pointer, where we start out here with just like work order, work order equals work orders, like so. And as we go, you know what I could do here just to make sure too? This would be an interesting way probably to prevent bugs. You know what I'll do? I'll do total work order count, or it'll be total tile count will be the number here. So we'll just say, okay, the total tile count is how many of these we're going to have, but the work order count will leave at 0. And then when I come in here, what I'll say is work order count plus plus will be where we are. We can assert here that the work order count is always less than the total tile count that we allocated, right? Just to make sure that we're not doing anything weird. So we have a work order we need to fill out. So here's the order. It's going to be the queue work orders plus the work order count. We're then going to fill it out with all of the values that we would have used to render the tile, right? So in fact, here they all are, right? We're just going to do these world equals world, image equals image, minx equals minx. Oops, that's, I guess it's xmin, and you know what? I guess these are, I named them differently. Don't ask me why. Right, and so all we're going to do here is just copy in these values. Like so. Okay. So that's the thing that's just going to go through and get us all of our tiles that we wanted into the work queue. So we just have an array of all of the things that we need to do to complete the image, like all of the tiles that we would need to render in order to complete the image. And then all I'm going to do is loop through them from, 0 to however many there turned out to be. And at the end here, I could also assert the equivalent. That it's equal, right? I'm going to go ahead to array.h. I like capitalizing assert myself. And I'm going to go ahead and include the default C runtime library assert. There it is. OK. And so I'm going to go through each of the work orders here. And I'm going to grab the correct one out. So work orders, like so. We're going to grab each of the work orders out in series. And then I'm just going to use the parameters of the work order, like so. To render the tile. Now, the work order itself is the other way around. I don't know why. But it is. So there we go. And now what we need to do is, now what we need to do is when we call render tile, we want to pass the work queue here because that has the accumulators in it now. So what I'm going to do is go up to our render tile call. Here it is. And when this goes to implement stuff, to increment stuff in the world, it's really going to increment stuff on the world, on the queue. That's where the stats will live. And it looks like I also have to change it in the printout, of course. There we go. That'll be in here and here and also here. There we go. And so now we're using the work queue, and it looks like everything's good. So you'll notice how I did this, right? I took a single-threaded program, and I never made it multi-threaded. I just did a series of steps to transform it into something that could be multi-threaded, right? So now we just have an array, and that array has all of the work that needs to be done. And what that means is now if I did have a way to launch multiple threads, I could actually make this work. So let's see how I would do that specifically. Here is render tile. What if I wanted to get rid of all of this stuff here, right? Well, what I could do is I could say, well, let's just do a while loop here, for example, that said while the queue, I think I even made a thing for it here. Next work order index, that's going to start at 0. While the next work order index is less than, or I should say, work retired, or total tiles retired, I guess I should say. While the tile retired count is less than the work order count, or even I could say total tile count, right? I know that we're not done. So while it's not done, I'm just going to call render tile. And I'm not going to do any of this stuff, right? I'm going to pull this out into a separate sort of thing, right? So out here at the top of render tile, I'm going to say, what if I just took all of the information that render tile was previously getting passed, and instead of that, I just actually pretended that I had a work order here that would tell me what it was, right? So I'm going to say, okay, let's go ahead and get, order world. Let's get image U32. Order image. Let's get xmin equals order xmin. Order ymin. Order one past xmax. Order, one past ymax. So if I did something like this, now I have all of the information that I actually need to get, right? And so all I need to know is what work order index I should use. And in order to know which order I should use, I actually have this next work order index thing here. So what I can do is take next work order index, use that to tell me which order to use, and do the rest from here. So now the render tile call itself is sort of like a multi-threaded thing that just isn't running on multiple threads. It can just take a queue, figure out which work order it's supposed to do, and it will automatically tell me when we're done, because every time I do tile retired count less than total tile count, I'll know that, you know, it was correct, right? Now the other thing I can do here is I can be a little bit more careful with this. I can take the next work order index here and say this is my work order index, like so. And I can say if, right, the work order index itself is greater than or equal to the work order count, so the total number to do, then I can just return immediately. I can just say don't do the rest of the thing, right? Don't do the rest of the function. So only if the work order that I got back, so this way even I can just keep calling it over and over again, and it's not a problem, right? So now we're just calling that one function. It's responsible for getting something off the queue itself, and it will work and do it, and off we go. Now you notice we've got a little, my head is in the way here, so we can't really see if we finished the last tile. So I want to just make sure that we're not missing a tile there. Is there some way I can maybe make this? There we go. There we go. I want to make sure we don't miss a tile. So there, that's good, right? Okay. I'd also like to print out the number of tiles. Okay. There we go. So we're currently doing 40 tiles, right? Which is not quite perfectly balanced for the number of CPU cores we have. We'd probably like the number of tiles to be equal to the number of cores, but who cares? We don't really know that that's true because each tile could take longer, or shorter, or longer. So there's that, but hold on one second here. What's the, let me see. All right, so what we would like to do now is we'd like to actually get multiple threads hitting that render tile function, right? So what I'd like to do here is say, well, okay, when we start up here and I do this work queue thing, I want to basically create, for core index equals 0, core index is less than blah, plus core index, right? And what I'd like to do here is actually say, well, I want to do the core, I guess, is it core count? There it is. I want to create threads. I want to create one thread per core to start doing the work here. The problem I have is that I don't actually want to create one per core because I still am in the main loop here. I want to have one core one core is this executing this, right? So I really want to I want to assume that core 0 is doing me, and then the rest of the cores will, spin up now, right? So what I want to do here is go through the core each of the cores. I want to create threads for each of these, and I want those threads to basically be able to call render tile. So I want to create a thread, and I want to pass this as the special value to the thread is going to be this queue here, right? And then the rest of this code should actually just work. The only thing that we're going to have to do, that we're going to have to change, is we're going to have to go look at these two functions here. These are going to have to be functions that will carefully update these values because they need to be told that these are, these are basically have to be locked adds, right? Because now these values are getting updated for multiple threads. They're actually the only values that are getting updated for multiple threads are these ones that I've marked volatile. So we'll do this. All of those volatiles have to be behind locked adds. The reason for that, again, is multiple CPUs are touching at once. The CPUs themselves, therefore, need to be told that they cannot just update what's in their cache. They have to go out and make sure that they have exclusive access to that cache line. To update it properly without stepping on someone else's value, right? So we have to tell them that it's a locked add. Okay. So those locked adds have to be in place, and I don't really like to use the term locked add necessarily because it doesn't say what's going to be the return value. And you can see in this case, in the case down here where we do locked add, I don't have to care too much about what happens because you can see this is just incrementing these values and nobody cares what happened to the actual value, right? But in the case up here, where I do a locked add, I actually need to know what the value was. And I want to know what the value was before the add took place. So I want to do a locked add and return previous value, right? Is actually what I want to call this function so that I know what's actually coming back from it. Because the other thing it could do is do a locked add and return the new value after the add. Now I don't care which one it returns me. I could compute either one by just doing a subtraction after the fact of the number that I know that I added. So they're really equivalent functions, but I just want to make sure we know which one it is so that you don't get little bugs where you think that you're calling locked add that returns the new value or locked add returns the old value, and it turns out you actually have the other one. So we're going to need one of these for each, right? We're going to need values that increment U64s. And, you know, when we look at this, we're like, well, if we wanted to make this program simpler, we could just only use U64s for this, right? We could say that we just do that. And if we wanted to do that, I would just end up with this, right? That's all there really is to it. And what I can do is I can just cast these down when we actually use it. The one time we use the tile retired, and it's no big deal. And the integral promotion, everything else should work fine there, I think. So that should just be, you know, totally reasonable. I'm going to stub this function out right now. And so these are the two functions that we really need to create. At the moment, we can just do this, but you know, we're going to have to do something better when we actually want them to work. Right? Okay. So our work order index is a 64-bit value now. I think that's the only change we actually need. Let me kill these dudes that are popping up there. What is the... Oops. Must return a value. Right you are, sir. So when we actually get the value out here, we want to return the previous value. So we'll grab out the value first, then we'll add to it and return the result. There we go. So now we have what I think, barring any bugs that we may have here, I have what I think would be a correctly written program for multi-threading without the actual multi-threading. And so what we need to do at this point is we need to have, and there is one thing we probably want to do here, which is, it's really not super necessary, but we probably want to just make sure after we fill out all the work orders and start creating the threads, technically we want to say here that there's a memory fence. Now, you know, technically, we might want to do that here. I don't want to introduce a separate memory fence. So what I can do is I could increment a dummy variable, right? What I could do is I could do a locked add and return previous value of one of these volatiles here. Let's say next work order index. Oops. And what I'm doing here is I don't want to introduce extra complexity to the program, which has, I don't want to define more stuff than I need to. So I don't want to rely on a fence, but I need a fence here. And what do I mean by that? Well, all of these work orders are getting written by core 0, right? Whoever's running the main code. And then I'm going to create a bunch of threads. Technically, core 0 is under no obligation to have flushed those actual results out. And so if another thread were to come along and look at the queue, it may not have actually flushed out the results that it wrote. So we want a fence there that just says, hey, complete all of the writes you were going to write here before those other threads start to come. Because technically, creating a thread is sort of not really a write. Now, it actually is a write that will be serialized because I know that Windows has to do writes to create the thread. So really, this fence is probably just not necessary, but I'm just doing it there to just be complete, right? Because create thread is almost certainly going to fence itself. And so you really don't need an extra fence here, but just to be extra secure, I'm just saying, hey, technically speaking, since there's no other writes happening subsequent to this that are multi-thread aware, you should probably write fence to make sure that the work orders all got filled out beforehand. That's all. So anyway, all we really need now is to implement these two functions. So I think we're pretty good to go. I need an address there. I think we now have a fairly correctly written program. We got to maybe pay a little closer attention to it and make sure it really is correctly written. But we should be good for everything else in the program now, except for the fact that we don't actually create any threads and we don't actually have a locked increment. So what I'm going to do here is, because I don't want to use the C++ runtime libraries thread stuff yet, because I'm not super familiar with it and I never actually use it, I'm going to first use the Windows ones, and then I don't think we'll have time today, but in some future time when I'm feeling like getting disgusting strewstrip all over me and taking a shower immediately afterwards, we'll try using standard thread just to make it so that this compiles on more than just Windows. I really don't want to do that. I really don't want to do that, but I will do it just for fun. So I'm going to include Windows here, and I'm going to have create thread actually do a create thread call. I'm going to call this, like, I don't know, create work thread, maybe, just to not conflict with a create thread call if we want to use the regular create thread call. Although overloading should take care of it, but sometimes they use macros and things like this. So I want to create a work thread here. So I'm going to go ahead and use the Windows call for create thread. Here's the function. So what I need to do is I just need to call this guy here, and it's relatively straightforward. I don't care about security attributes. I can use the default stack size. We need the starting address here, which is going to be the worker thread function. We need the parameter, which is the one that we've passed here. We need the creation flags, which I don't know if there's anything we actually care about. I don't think we do. We can just let it go. We don't need to suspend it or anything. And we need to know what the thread ID is. We don't really need to know what the thread ID is, but, you know. So we'll go ahead and grab the thread ID here. Like so. And I think we can close the thread handle immediately afterwards because I don't think we care about it at all, right? So in theory, that's all fine. That should all work, I think. And there shouldn't be anything particularly saucy going on here. Yeah. So that should create a work thread. We just now need a function that uses the sort of the thread start routine, right? We just need to go look up what the thread start routine definition is so we can make a callback there that Windows will call us back at. That's not what I wanted. There it is. This is the thread. So as you can see, all it is just something that passes that one parameter that we have there to us as a void star. This LP void is just, I don't know why they insist on defining everything in Windows, but there's the thread callback. Looks like that. So when we create the thread, it'll get called back here with the parameter. We know that parameter is our work queue. And so all we have to do here is just call our actual function that we wanted to have happen, which is render tile, right? A lot of jumping around there. So I'm going to go ahead and put this here and be like, to do Casey, when I feel like taking a long shower afterward, go ahead and port this to standard thread, maybe, no promises. So anyway, we need to have this called render tile. So what we want to do here is inside the thread proc, we want to call render tile on the work queue. And what we'd like to do is we want this thread to run for as long as render tile could potentially do something, right? So render tile right now doesn't return anything. What I'd like to do is make it so render tile does return something, right? So in this case, it'll return false. In this case, it will return true. So what I'll do is I'll just say while render tile, off we go, right? So we'll just keep calling render tile until it returns false, which means it couldn't do any more work. And at that point, we'll just return out of the thread and say we're done, right? And that's all it's going to do. OK. So I forgot to name this worker thread, but now it should be correct. Yeah, I got to fix this function here. So whenever we succeed in rendering a tile, I'll do the printf, because otherwise it's going to end up at the end when it's waiting on the last tiles. Other threads may have taken those tiles, and we just print out raycasting a ton of times. So I only want to print it out if we actually finish the tile, just to gate that a little bit. So off we go. And you can see now that the speed has improved rather dramatically, right? If we don't create worker threads, so if we don't multi-thread our system, we're much slower. Let's take a look at the total time here, right? It took us 4,063 milliseconds to compute our image, so about 4,000 milliseconds or 4 seconds, right? If we do multi-thread, it takes 823 milliseconds, right? So if we look at the speed up there, it's about 5x, which isn't bad, right? That's not bad. Now, we don't know that this is working properly yet. It's kind of just accidentally working properly, probably. And the reason for that is I haven't implemented the locked add yet, right? So if we take a look at locked add and return previous value, this is still it's not actually safe. It's not actually doing a locked add. So to finish our program, we just need to do interlocked add here, right? So here's our windows. Here's the interlocked API. What I want is an interlocked add, interlocked exchange add. That looks good. The value of this variable will be replaced with the result of the operation. That's what we want. The function returns the initial value of the parameter. So this is exactly what we want, is interlocked exchanged add. We want the 64-bit value version, so we want this one, but this is exactly what we want. So inside here, what we want to do is an interlocked exchange add. Here's the value that we're actually using. They named these opposite. Sorry about that, folks. Just my bad there. And the result comes out here. So now it's an actual interlocked add. Looks like, because yeah, we're not a long 64, we're a U64. Those are going to be equivalent in terms of behavior, so we should be able to cast that just fine, like that, and off we go. So hey, that's pretty good. We've got a 5x speed up just from multi-threading, which is great. We might be able to get more out of that. I don't know. Let's take a look here. So you can see we got about 790 milliseconds to render the whole thing. 820, 836, 816. So we're hovering around the 800 millisecond mark there, right? And now I don't know whether or not having more or less of these tiles would be better or worse. And I don't know that we've really got a completely well-functioning program at this point either. I also don't know what the optimal number of cores is and blah, blah, blah. So we haven't done a lot of the work that we might want to do to make sure that all of this is working properly. But that is neither here nor there. We've done a reasonable job for just 2 hours of work or whatever. We're at least in sort of okay position. What I would like to do here is just say like, hey, maybe we should double check some of these tile counts or core counts here. Let's try setting the core count to only be 4 and just see what the effect is on the image. So you can see that it definitely got slower in that case. Let's try making like way too many threads and see what happens. That didn't really affect the time, oddly enough. And I guess that's just because Windows just, hey, it's smart enough to, each of our threads is doing as fast as they can. Windows is smart enough not to start up those other threads, I guess. I don't really know. But it looks like there's not a lot of gain to be had here by fussing with the core count specifically. It looks like the number of cores equal to the number of actual cores is about right. It produces about the right number here. Now, in terms of the tile width and height here, I'm interested to know if I just kind of fuss with it a little. Is there anything, like let's say I change it around, kind of arbitrarily poke at the tile numbers. Do I get much of a change there? And I don't know. It looks like, not really. It looks like maybe a smaller tile is a little bit better. The process cannot... What file is being used by another? I don't know what that's complaining about. Yeah, I have no idea what that was complaining about. But it looks like maybe there's a little bit of a win to be had there with smaller tile sizes. I'm not sure. But that looks like on average it is faster, right, with a smaller tile size for whatever reason. I have no idea why. Better, finer grained multi-threading perhaps. But it does look like, if you kind of drop that tile size down a little bit, maybe because you can get more at the end, like, there's a sort of this concept of drain out, right? Just to kind of give you some perspective here. Oops. So we're going through here and we're doing these tiles, right? And we're retiring tiles. At the end, there's some tiles left over. If there's only 2 tiles left over here, but I've got 8 threads, well, one thread's going to pick up this tile, one thread's going to pick up this tile, and then 6 threads are going to sit around doing nothing, right? So the smaller the tiles are, the smaller the individual work unit is and the less tonal drain out time there is. Because let's say each tile takes, 10 milliseconds to compute, right? Or something like this. If each tile takes 10 milliseconds to compute, then that means during this time here, I'm going to wait 10 milliseconds of drain out because the other 6 threads can't do anything. And so we're just waiting for the 10 milliseconds for each of these to compute. If I make the tiles smaller, right, so that each one of the tiles only takes like 4 milliseconds to compute, then even when I eventually get to the end and end on if there was only 2 tiles, then the ending is only 4 milliseconds that can't be overlapped, right? So the total amount of time that can't be overlapped is equal to however much time it takes to do one work unit in the worst case, because at the end, when you get to the end, you can't divide up that work unit any smaller. So even if there's, if a tile takes however long it takes, even if there's a ton of threads sitting around with nothing to do, they can't help on that tile at all, right? So making the tile smaller makes the worst case unoverlapped time smaller and smaller and smaller, so as you get to the end you avoid that drain out. However, you do have overhead in the dispatch, so that overhead in the dispatch does get worse as you go. So you can't just make them arbitrarily small. You can't make them 1 pixel, because the overhead of dispatching the pixel then becomes, that locked increment and all that stuff starts to get in the way, right? So, just something to be aware of. So we may want to just sort of prescribe the tile height here, like since we included windows, we can also get that core count in here. Oops. So what I can do here is just have a thing which is like win32 get core count. I can't remember what that is. This is not what I wanted. PS, not what I wanted. Win32 get CPU count. We already did this in Handmade here. I should just look in there. It's not get current processor number. And I don't really need to know about NUMA groups at the moment, because we don't have that kind of... NUMA groups are not... that stands for non-uniform memory access. And the idea is there are sometimes you have like processors that have localized memory to them. So like, 1 gigabyte of memory is closer to this processor and can be accessed by this processor more quickly. Another gigabyte of memory is more close to this processor, and you want to manage that. So you put the memory and the processors together so that they're not like split. You don't have this processor using the memory that's closer to that processor and vice versa. So non-uniform memory access groups are important in certain services. In this case, we just don't have that because we're not really sharing memory in that way. But that's what that is. Let's move this over here. So I just want to get this. Can you just tell me? I just want you to tell me how many processors there are. That's all I wanted. I'm just going to use this. So I'm going to use VW number of processors, and for now we'll just call that good. So here's the system info. Get system info. Because I don't remember how to get it on Windows. Number of processors. Done. Oops. So let me just take a look at what that actually gave me, because I don't actually know. Oh wait, we are printing that out. Never mind. So that correctly got the number, so hey, that's good enough for now. So this way, if we ran it on a, maybe some of you at home have saucier machines than I do that have like 32 cores or something. That way we would create more threads in those circumstances, which is what we would like to do. So that is the multi-threaded version of the situation. And yeah, so we're now pretty well multi-threaded. So what we need to do now is kind of extract this part out a little bit, sort of make it clear what's Win32 and what's not. So I may do that. I might just say, you know, because I hate the C runtime library and I strongly dislike the C standards committee and sort of their bumbling around. So I really don't want to be involved in that. So I might just make a Win32 Ray .cpp and put these functions in there. And make it someone else's problem to port it to their disaster. So let's go ahead and put these in here. So this is all we really need to do here. And what we can do is sort of define the functions that we actually care about in ray.h. Where is that interlocked guy? Ah, we're behind my head. No, okay. So in theory, that should be good. All we now need to do is actually use that Win32 bit in there. And so all we need to do here is say like, all right, we need something here that just tells us which of these things we're going to include. So we can say like, you know, maybe at the bottom, we'll just say include Win32 Ray.cpp. And we can even do this in the build here. We could say -d Win32 equals 1 or something like this, right? Ray Win32, pound if right? And then like something like this. So if I don't have one in the build, oops. If I don't have one in the build, it'll say you need to define a platform. If I do have one in the build, it'll be fine. And then people can port those functions as necessary. Now, the Ray Win32 thing here, one of the things I would like this to have a last error situation. I think probably. So I'm going to go ahead and crib off the Handmade Hero build here. And do one of those last error jumps. So after we do the compile, I'm going to do a set last error, and then I'm going to do a jump around it. So where's the last error here? I want to do one of those last error jumps. So I'm going to put a thing here that like jumps around this thing that runs the actual ray tracer. So what I'd like to do is jump around that last error. Now, I guess we don't do that in here anywhere, and I forget the syntax. Batch file jump on last error. Oh boy, I'm on Stack Overflow. This may go poorly. I just want the if. No, I don't want this. Is not what I wanted. This is not what I want at all. I just want the jump call. I just want this. So I assume I can do if last error go to no streaming, or go to end, right? I assume? I don't actually know. Do I need a then in there? Let's see. I hate batch file syntax. So I guess I can just do equals equals 0. I don't know. Or not. Do I have to do that? Okay. So let me see now if I insert an error. That didn't work at all. What does last error equal? It equals 0. So why did... Oh, I guess I want not equal to 0. Is what I actually want. So I'm assuming I can do a not there. Yeah. So I can do an if not. But it does equal 0. I don't understand. There we go. All right, we finally got the magic. So I just wanted to, since we had some extra time, I just wanted to make it so it wouldn't run the program anymore if we weren't actually using a valid program. All right, so now we should be able to crank up the, oops, that's not what I wanted. We should be able to crank up the ray count here a bit for each of the tiles. So if we want to do rays per pixel is like something high, the multi-threading should help us here. So you can see it still runs pretty quickly. Like it's, you know, it's certainly a usable speed with, and we never, like that would have taken forever before. Because 256, which was, you know, even half of it was like barely working, right? So just the multi-threading alone gets this up to a much more usable level, which is nice. And that's a pretty smooth image, you know, like that's super usable. We haven't put in like actual like, we haven't put in any kind of real light transfer, so it's a little iffy. In terms of how slow that will become, but at least we're getting better here, right? Yeah, and so that's nice. It would be nice to put in a better random number generator, certainly, but I think we're basically out of time. So I'm going to go ahead and go to the questions, and we'll leave it at that. Let's verify that our sort of here. Let's verify that our sort of test runs well if I run it from the command line, like the printout still works properly. So it should like show us a percentage here cleanly, right? And print out properly and all that. Off we go. And we should have, we can sort of see, here's our first day's one. You can see that it gets a good bit smoother on our next one, right? If we were saucy, we could like try to write out as well like what the timing count was. So maybe we'll do that. Let's just add one more thing real quick while we can. Inside the work queue, let's parameterize like the rays per pixel and the bounces, right? So let's use queue rays per pixel. What I might do here is actually, let's just do it this way. So that way the rays per pixel is set that way, and the bounce count will be the same. Also, I should put what you do in here. Just so we remember, there's a thing with needing to randomly terminate it. It's a long story. We'll discuss that someday when we do better light transport. So if we set the max bounce count and the rays per pixel both in the queue, right? Queue max bounce count is 8. Queue rays per pixel. Let's go 1024. The reason I wanted to do this was because I'd like to print it out. And I'm going to move the clock down to past the business. So we're just going to do basically everything after the sync. Right, so we're just going to time this part of it. So I'm going to go ahead here and say configuration is this. Quality is rays per pixel, bounces. So now when we run it, it should give us like all the information that we need, right? And it does. So it's like says 1024 rays per pixel, 8 max bounces per ray. Maybe I should rephrase that to 8 bounces max. And I think we're good. I think that's sufficient. And so now, yeah, we can produce a really nice and smooth image, right? I mean, it's pretty good. And, you know, mostly we're just in want of lighting now. That doesn't take very long to do. And the other thing is we haven't SIMD'd yet. So the next thing we can do is make it SIMD. And I think that will improve it quite a bit. So I think that's all good. Let me go ahead and we'll save an image off for this as well. Yeah. All right. So let's go ahead and go to the Q&A here. Dotor, could you please make a portal changing the ray position and orientation upon hitting the portal to come out of the second portal? Nah, that's, I mean, if we ever do geometry stuff, sure, but that's kind of not really in line of what we're doing here. Cyanox, do you assume the x86 memory model in your code? I assume x86 ARM, basically, because there's nothing else to run on anymore. Game code or server code doesn't run on anything other than those two processors, so that's the memory model that I tend to assume. What about const, volatile, and register together in a single declaration? Register is ignored. Register doesn't do anything anymore for most compilers. Okay, let me just get one more thing done here. Let's close this down. I'm going to go ahead and do build Ray. Oops, no. I'm going to do build Ray to 2017 10/22 second day image dot text. I suppose standard error should really print out so that we can capture the output that's the stats and have standard error still print out the rest of it. You know what? I took it back. I'm not quite done. Let me do one more thing. So let me just print to standard error the status stuff. Like so. And that way we can pipe the results if we want to capture them. Configuration and quality and all that stuff should go to standard printf. All right. Let me see here. So I assume that'll work properly. I'm not 100% certain. Let's take a look here. So let's go to data now, build ray.exe, and that. And we'll see if we get, yeah, there we go. So I just wanted the status to always print out here, and all the rest of the output goes to standard out. What is the difference between path tracing and ray tracing? So really, those are kind of just like arbitrary terms, because path tracing still does do ray tracing, but they're generally used to distinguish the difference between a ray tracer generally just is forward doing bounces where it casts out a ray, sees what it hits, casts another ray, sees what it hits, casts another ray, right? And it doesn't really consider the whole path in any particular way. Path tracers actually do. So what a path tracer, there's a couple of different kinds, but what a path tracer might do, for example, is take a start, the camera, and a light source, and do ray casts that try to connect the two of them together. Another way might be to start with a ray tracer that produces a bounce that goes from a camera to an emitter, but then after it goes from a camera to an emitter, it will permute the path by taking things in the middle of the path, like bouncing in the middle of the path, and reshooting to try and connect those two, right? And so a path tracer generally implies a ray tracer that thinks about the whole path somehow in a way that just straightforward bouncing wouldn't do. So it tries to do some permutations or some multi-sided, like bidirectionality, things like that. It will try to take this into account, right? So, like a very sophisticated version would be like Metropolis light transport, for example, where it finds a stable path and then does permutations on the path based on probabilities that it thinks that will create likely contributions to the lighting equation as proportional to their value, proportional to their likely contribution. There's things like manifold exploration, where they'll try to take one path from an emitter to the camera and figure out the boundaries around where the various paths could work for that emitter to hit the camera, right? So there's like a bunch of things you can do there that are like sophisticated ways of treating the light transport exploration that don't just randomly bounce around the scene. Now that the raise per pixel and max bounce count are parameters, you could potentially give different tiles different settings to compare quality side by side in the same image. That's true, you could. If you wanted to, you could put raise per pixel and max bounce count. You could put those into the work order if you wanted the different ones to be different. What do you think about OpenMP? I've never used it. What is SIMD? SIMD is SIMD, single instruction multiple data. It just means utilizing the fact that modern processors, both ARM and x86, or x64 I should say, although x86 had it as well, they both have the concept of wide instructions, which are instructions that do, for example, a floating point multiply. They do 8 numbers times 8 other numbers at once, or 16 numbers times 16 other numbers at once with a single instruction. And so if you got perfect speed up by using those instructions, you could have 8 times faster or 16 times faster execution of your code, or 4 times faster if using the older SSE stuff. AVX2 and AVX512 are the 8, they go 8 and 16 wide. That's a good way to increase performance of your code. You usually don't get the full 8x or 16x because usually there's a bunch of stuff that's not expandable to the full width and there's work that has to be done there. So you don't typically get a full speed up, but you do get a significant speed up usually. And so that's what SIMD is. Do you get effects like bloom or lens flare for free if you implement more realistic camera stuff? Yes, if you leave those scare quotes on for free, you do, but it's important to know what those scare quotes mean. So if you implement a real lens and film aperture, then bloom and lens flare and things like that will happen automatically. The problem is that it isn't free in terms of computation, right? So things like bloom happen because of halation on the image plane. And that means you have to actually raycast halation rays, right? You have to actually penetrate the film back and bounce back up into the film substrate. For things like lens flare, you have to be accurately modeling the optics of the lens through the glass in multiple places in order to get the flare to occur. So, it's for free in the sense that if you model everything accurately, you'll get those effects, but it's in no way free in terms of sampling cost. The sampling cost goes up dramatically in order to capture those effects because you have to actually simulate those things. So oftentimes it will behoove you to not do them 100% realistically anyway, because you'd get a lot faster image for the same quality as if you tried to actually simulate like real halation. Isn't uniform random sampling bad? I thought you need to use blue noise or process sampling or something. Yes, uniform random sampling is not a good idea for 2 reasons. One is because, you would like to use sampling patterns that are more suited to avoiding ringing artifacts or banding artifacts or things like that. So yes, and also the other thing that's bad about uniform random sampling is right now we are not doing any work to try and get the samples to properly sample the space based on importance or anything. So generally speaking, as you go and implement better material handling, you're going to want to put good sampling in there, right? We are not doing any of that. Cyanox, ARM memory model is extremely relaxed though. I don't think it's extremely relaxed. ARM has a pretty reasonable memory model. So you mentioned that hyperthreading can schedule instructions on separate ALUs of the same core. Did I hear that correctly, or did I misconstrue what you said in my mind? I'm not sure exactly how to interpret the question. A core has some number of ALUs on it, right? So if you take a single core, let's say it has 2 units that can issue a multiply. So it's got 2 multipliers on it or something, right? Whatever, I'm making this up. So let's say it's got 2 multiply units on it. Then what that means is that if I'm looking at the instruction window for one of my threads and I see 2 multiplies that I can issue them both and they'll just go start doing the work. But then if I need to issue a 3rd multiply, that multiply can't issue until one of those other multiplies completes because there are no more arithmetic logic units available. So if the instruction window is large enough, and there's enough multiplies stacked up without other things happening that might block them, then a single thread can utilize all the multiply units of a core and you don't have to worry about it, right? However, if there's stuff in between there that would stall it, so there aren't enough multiplies to feed the number of multiply units that are there, then what hyperthreading could do is it can look to the other thread on that core. Because hyperthreading, remember, there's 2 threads on a core, right? It can look at the instruction window from the other thread, and if that one has a multiply, it can issue that multiply on the ALU that is currently fallow. So what you can think of hyperthreading as doing is hyperthreading is basically a way of pulling instructions from 2 threads at once based on what is available on the chip to execute. And this is true for things that are not ALUs as well. Basically any execution port on the CPU that can do something, if it can find an available ready-to-execute instruction on either of the 2 hyperthreads, it can start utilizing that instruction port that otherwise would have gone fallow because the other core just doesn't have a need for it, right? And so that's what hyperthreading does. Would you change anything if you were using a Ryzen Threadripper CPU that has 4 core complexes? No, but only because I have never programmed a Ryzen Threadripper before, so I don't know what its behavior is like. When I get more experience with that CPU architecture, I may have more opinions on it, but at the moment, I wouldn't suspect you need to do anything really much because this is a pretty simple multi-threaded program in that the cores are completely, the threads are completely disaggregated. They don't share memory almost at all. So in theory, you shouldn't have to worry too much about the underlying architecture because this is a very simple program. Typically, you only need to start thinking about other architectures really hard when you have a lot of memory sharing or complicated stuff happening. Can you give a quick overview of how important sampling works? No, because it's very complicated. Why were you trying to kill me? I was working very hard. From Raycaster. Because I needed to make changes to you. Could you maybe do a GJK implementation on a test stream sometime? Maybe in the future, but that'd be a ways off. Is AVX2 common enough to use it in a game? Probably not at this point. It's common enough that you might want to use it in advanced features in a game. So for example, if you have an ability to test, you could just look at the CPU, does it have AVX2, use this fast path for some extra bonus feature like better blah or whatever, like faster physics, more physics, I don't know. But whatever you're doing, if it's an optional feature you can turn on and off, that might be a reason to use AVX2. I wouldn't require it. Unless you're just unless your game already requires a CPU so powerful that you know it will always have it, right? Which you might already be doing that. So you have to kind of make that call there. Will the ray tracer program in the future use GPU to do the ray traces? Nope. Where can we find the code? The next time I update the Handmade Hero code, so next weekend when I upload the next day of Handmade Hero code, it will be in the repository and the downloadable. Wouldn't it be more sufficient to make an entry for each ray to split up the work more evenly, and also this could work on the GPU? No, you never want to go per ray. That's too granular. So the amount of overhead and dispatching per ray is not good, right? You need to have a much bigger bundle than a single ray, because otherwise the overhead of work management and dispatch becomes dominant, and you don't really want that. How much different is this ray tracer to those that with live previews where you see the image get better starting low res and go higher and higher. I assume they don't render line by line. So the way you would do that is you just do 1 ray per pixel for all pixels and then go back and do another pass, right? So you're constantly doing 1 ray per pixel over and over and over. And so right now, right, like you can see the way that we're doing that in here. We've got a loop, rays per pixel, right? And we just accumulate the rays per pixel and then output a single value. What you do instead is you save this final color plus contrib sample. What you actually do is you make final color be, you basically make an image that's a float image, and you do this contrib every pass, you do that accumulation, right? And then you just, every time you finish one pass of the image, 1 ray per pixel, which is relatively quick, right? You output a new preview. That's the only difference. Are there any things that you need to do to take advantage of hyperthreading CPUs, or do you treat threading the same as a non-hyperthreading CPU? Yeah, you don't really need to do anything specific. For this usage case, because of the memory pattern is very simple. If you have more complex memory patterns, you do have to think about it, because since cores, 2 hyperthreads on 1 core share a cache, they share at least the L1 cache and probably the L2 cache. So what that means is that in that scenario, you want to make sure that those 2 hyperthreads, as much as possible, are using the same memory areas. So if you have a more complex memory layout and usage than we have in this example, where you're actually caring about how cache utilization is working, meaning if you have a work set that's bigger than the cache, then you want to try and keep things that use similar memory access patterns on the same core. So those 2 hyperthreads should be similar memory access patterns. All right, so someone was asking about the memory order was posting a thing for ARM memory model. Let me open that up real quick here, and then I'm gonna end the stream. Here we go. Do 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 do. There's a lot of, this is a bit big. You said page 20, so hopefully I can skip to just page 20 here. Where is that? This is not a very concise summary. Where am I supposed to be looking? This is way too big. I don't really need this. The only thing you care about is whether or not it reorders around a locked increment, right? That's it. If it doesn't reorder around a locked increment, that's all you need to know. Sorry, like a locked instruction, right? So whatever its compare exchange instruction is, if it doesn't reorder around the compare exchange, you're pretty much done, right? If it does reorder around the compare exchange, then you have additional issues to worry about. And so that's most of what I would say you care about. If ARM's memory model is relaxed enough that it reorders around a compare exchange, then I would just, which I don't think it does, but if it does, you just include a barrier, you include a fence when you call that function, and then you're done. So that's really all you need to know about the memory model, because I'm pretty sure ARM will not do that, right? It will not reorder. It's trivial to just fence your mutex, and then you're done. So the only CPUs that were really weird is like the PowerPCs and things like that, where you had all kinds of weird sorts of read things you had to manage and just strange things going on. And those were just, yeah, nowadays you really just don't have to worry about that particularly much, I don't think. Page 349. Okay, I'll take a quick look. 349 is, where is 349? Nope. Nope. Let's see. Dependent loads reordered, atomic instructions reordered with stores. Here we go. So ARM64AR is the one we're looking at here, I assume. The rest of these we don't care about, right? Like MIPS, whatever. So it looks like with atomic instructions reordered with stores is the one you care about. So I would say all you have to do is, like literally all you have to do is just put in the fence, put in a store fence, and I'd probably put in a load fence too. A load fence and a store fence right next to your atomic increment, your atomic exchange. And then that's it, right? You don't have to worry about it, assuming that they allow you to do that. That's really the only thing you have to do. And then you're pretty much done. Because that's what you worry about on x64 as well, or AMD 64 is what they call it on this list, right? And then you're good to go. And like I was saying, you just want to make sure that your interlock function does that. That's all you need to do. And then off you go. I generally don't. I try not to write code that cleverly works without an interlock function, if that makes sense. Not so much, I guess, because I'm worried about ARM or something, but more because, or, a weaker memory model than x64, but more just because I find that I may miss something in that case, if that's, I feel like it's too easy to be overly clever and then make some change to code and forget that will break it or something. So I generally try to make my stuff work with a compare exchange, and have that be a sync point where I just assume everything's synchronized at that point, and I don't assume anything in particular happens outside that point, because I find that if I try to be more clever than that, which you can be, right? Especially on x64, you can be way more clever than that, because it basically has extremely enforced memory ordering most of the time. Like it's the most enforced you can pretty much be. You can be way clever than that. I just don't tend to do that because I feel like it's too easy to make a mistake and think that you did it right, but you really didn't. So I don't really tend to do that code. And I tend to assume that my locked increment will include a barrier, which it automatically will on Intel in all cases. But yeah, it looks like maybe ARM doesn't. I didn't think that was true of ARM, but it's been a while. So I'm actually surprised at that. I didn't think they did do that reordering, but maybe they do now. So, next time I program an ARM, I'll take a look. All right, so what we also should, I guess, I'll notate that as well. So there we go. All right. I think, oops, did I not save that for some reason? There we go. I think that's it for today. I'm going to save off our second day image here as well. So our first day's image and our second day's image are really no different other than the fact that we sped it up quite a bit. And I also saved here what the configuration was we used. So we know we have 8 cores. C4 series of tiles, we did 1024 rays per pixel with 8 maximum bounces. The total number of bounces that we ended up recording was this many. And here's our performance per bounce, right? And so we think we did all of that correctly, hopefully. And, you know, someday when we decide to do a little bit more work on the ray tracer, we can implement better lighting calculations, and we'll see how that affects it. We could also SIMDize it at some point when we're in the mood to make it SIMD, and then we can make it again maybe 4 times faster or something like that, hopefully. So we get another speed boost there before laying in a bunch of gnarly math computations for doing our images, right? Anyway, that's it for Handmade Hero for today. Thanks everyone for joining me. Next weekend, I think we'll go back to doing regular Handmade Hero programming, where we'll try to get some lighting again, actually. Working in the game now, which we wanted to do GPU accelerated, which does a little bit of raycasting actually, just not for the entire image. So we'll be back on that next weekend. Hopefully you'll be here to join me for that. Until then, keep in mind, if you would like to play around with Handmade Hero source code, and I will, next weekend when the source code gets updated, I will also include the raycasting source, so that if you want to play around with that, you can always pre-order the game on handmadehero.org, and it will come with all that good stuff for you. We also have a forum site if you want to ask questions. We have a Patreon page if you want to support the video series, a schedule bot that tells you when we're going to be live, and an episode guide you can use to catch up on old editions of the series. That's it for me. I will be back next week. Till then, take care, everyone, and I'll see you on the internet. Take it easy, everybody.